Topology. It is a kind of math in which we study shapes. You might be wondering, wait, isn't that geometry? Well, you're partially right, but there is a minor difference between both. In geometry, we also study shapes, but we are more concerned on finding the exact measurements of these shapes, while in topology, these distinctions don't essentially matter to us. In topology, we pretend that all the shapes we deal with are made of squishy rubber. This is useful for studying crazy shapes like high-dimensional objects or weird twisty knots in particular. To a topologist, there's no exact difference between a square, a circle, or a weird-looking circle. There's this logical joke that is common among topologists that illustrates this difference. A topologist is someone who can't tell the difference between a donut and a coffee cup. Imagine this, your coffee cup is made of squishy rubber. Then when you finish drinking your coffee, squish the cup part, collapsing it into itself, leaving only the handle, which makes it identical to a donut. Now, is it possible to change a cube into a sphere by similar deformation without cutting or gluing? Pretend that we have a latex balloon cube that's firm enough to stand without air. If you blow air inside it, the cube will expand, ending up with a sphere. This type of deformation is called a homeomorphism, which we're not allowed to cut or glue any part of the initial surface. You may ask, how do we know which surfaces are homeomorphic to each other? Let me introduce to you the Euler characteristic. For any given surfaces, the number of vertices minus the number of edges plus the number of polygonal faces is known as the Euler characteristic. For example, the Euler characteristic of a tetrahedron cube is 2, since V is 4, E is 6, and F is 4. In fact, all convex, polyhedral like cubes and other prisms have the same Euler characteristic too. One of the topological percepts is that two surfaces are homeomorphically identical if and only if they have the same Euler characteristic. Euler characteristic can also be calculated for surfaces without even edges or vertices, using triangulation. Making a spherical surface spiky is all it takes to triangulate it. To do so, we decompress a round surface into a polyhedral surface. Then, we can draw lines that divide the faces of these prisms into triangles. Since the new surface is now comprised of various triangles, counting the vertices, edges, and triangular faces is easy. Now, why do we care about homeomorphism and why is topology important? It turns out that if two surfaces are homeomorphic, then all topological properties are shared by them. An example of a topological property is simply connected, meaning that any surface loop can be shrunk down to a single point. For the second question, surprisingly, topology has many applications to physics, biology, and other mathematical areas.